In this video, we discuss the material in Chapter 12, covering unsaturated hydrocarbons, looking first at alkenes and alkynes, and then moving on to aromatic compounds. Unsaturated hydrocarbons are carbons that include double bonds and triple bonds and ring delocalized double bonds, which are aromatic compounds. Each of these three classes of unsaturated hydrocarbons has their own nomenclature and reactivity. We'll begin with alkenes. Alkenes are hydrocarbons that contain at least one double bond between carbon atoms. The molecular geometry around the double bond is trigonal planar, with bond angles of roughly 120 degrees. So if you think about this, with carbon having four bonds, if one of them is a double bond, then we're going to have three electron groups, or three electron domains, and that corresponds to the trigonal planar molecular geometry. Alkenes also have two fewer hydrogens than their corresponding alkane, making them unsaturated with respect to hydrogen substitution, or hydrogen binding to the carbon. So you can see here we have our formula structures for an alkene, and this is the simplest alkene ethylene. So in A we have our condensed structure showing the double bond between the two CH2 units. CH2 is sometimes called a methylene unit. In B, we have our full Lewis dot representation, and C is our ball and stick model, showing our 120 degree angles. Now, as you can imagine, the two bonding pairs between the carbon-carbon interaction here, we have more electrons there, and they actually push out further in electron repulsion. So from a VS-EPR perspective, the hydrogens are actually pushed closer towards one another. And so typically that bond angle is less than 120 degrees, while the CCH bond angle is greater than 120 degrees. Alkynes are hydrocarbons that have at least one triple bond between two carbon atoms. Now, if we think about this, with carbon having four bonds, if one of them is a triple bond, then it will have one other bond to it, which could be a carbon-hydrogen or carbon-carbon bond. And thus we have two electron domains, or two electron groups. Therefore, our system is going to be linear. So alkynes have linear molecular geometries with a bond angle of 180 degrees around the triple bond, and they have four fewer hydrogen atoms than their corresponding alkane for that given carbon-carbon group. So we are unsaturated relative to the number of hydrogens that we can have. And in our figure below, we have what we call ethine, or more commonly called acetylene. So acetylene is C2H2, and you can see the condensed structure, the Lewis dot structure in the center, and our ball and stick model. And of course, acetylene then would have four fewer hydrogen atoms than ethane would have. So it is unsaturated with respect to the number of hydrogens. Now, for alkenes and alkynes, the overall shape of the molecule depends on the shape at each carbon within the chain. Now, at any given carbon within a chain, or and within the structure, if it has four bonds, the shape is tetrahedral. If the carbon has a double bond and two single bonds, then the shape there will be trigonal planar. If the carbon is part of a triple bond, then that shape is linear. There are cases where you have two carbon-carbon double bonds next to one another. In that case, that carbon can appear linear. The general formula for alkenes and alkynes, I think you can straightforwardly deduce. So, for an alkane, we have linear alkane, or a linear branch, we have CnH2n plus 2. So alkenes can be expressed as CnH2n. We've lost 2 of the hydrogens. And then for alkynes, we have CnH2n minus 2. We've lost 4 hydrogens. A 4-carbon alkene has the general formula C4H4 times 2. That gives us C4H8. So C4H8 would correspond to a butene. And then if we have a 4-carbon alkyne, then it's C4H2 times 4 minus 2, or C4H6, and that would be butyne, as we'll see later when we name these structures. So from the table we can see that alkanes are CnH2n plus 2, cycloalkanes are CnH2n, alkenes are CnH2n, and alkynes are CnH2n minus 2. The names of alkanes, alkenes, and alkynes all use the same prefixes to indicate the number of carbon atoms in the longest chain. The suffix for alkene names is -ene, and the suffix for an alkyne is -yne. Thus, propane, which is our 3-carbon alkane structure, when we convert this to the corresponding unsaturated systems, we have propene or propyne for the alkene and alkyne respectively. Now, if we have longer chains, the location of the double or triple bond has to be specified. Now, for propene and propyne, of course, there is only one place for the unsaturation to be. But for non-cyclic hydrocarbons with more than 3 carbon atoms, we have to indicate the location of the double or triple bond using a number. And what we do is we choose, again, the longest chain that contains the unsaturation, that is the double bond or triple bond. And then we number it such that the double bond or triple bond is located at the lowest number position. So we have 1 butene and 2 butene shown here in the figure. We, of course, would not have 3 butene because that would give us the incorrect number usage. Now, just like we had substitutions on alkanes, alkenes and alkynes need to have their substituents enumerated. So the nomenclature for alkenes and alkynes are similar to the alkanes that we looked at, except the parent chain is not the longest continuous chain, but it's the longest chain that includes the double or triple bond. The parent chain is numbered such that the double or triple bond has the lowest number, and then the position of the double bond is given before the parent name of the compound. So here let's take an example. In this figure you can see that there is a 5-carbon chain, but that does not contain the double bond. If we include the double bond, that is a 4-carbon chain. And in this case, that 4-carbon chain then would place the double bond at the 1 position. And when we do that, then at the 2nd carbon we have an ethyl group. So this would be named as 2-ethyl 1-butene. And make sure to put your dashes in between numbers and letters. Another thing to consider with alkenes is what we call cis-trans isomerization. Okay. Now, cis-trans isomerization is a type of isomerism. And one thing to understand is that double bonds do not rotate. Single bonds can rotate. We looked at this before. If you have, for example, you can take ethane as a structure. The CH3 units can rotate like propellers. If you have ethene, the double bonded system, those hydrogens are fixed. The molecule, in fact, is flat. It's flat like in a plane, and the hydrogen atoms do not rotate. So because of that, positions become fixed. Now, looking at figure 12.5, here's the case of 2-butene. There are actually 2-butene structures that are distinct. These are two different molecules. And in fact, you can buy bottles of cis-2-butene or trans-2-butene. In the cis-2-butene, the methyl groups are on the same side of the double bond, as are the hydrogen atoms. In trans-2-butene, the methyl groups are on opposite sides of the double bond. Likewise, the hydrogen atoms are on the opposite side of the double bond. So it's important to understand that this is a type of stereoisomer. All the atom connections are the same. You have the same types of connections for every single atom in the group, but they are oriented different in space. So when we have a different spatial arrangement, this is what a stereoisomer is. Something where the atoms are different in space, like enantiomers. So cis-trans isomers are not structural isomers. They are stereoisomers because they can't freely rotate around a double bond. Next, we're going to look at the chemical reactions of alkenes. There are 3 reactions that we'll consider. The first one is the substitution reaction, where some hydrogen atoms are replaced by other atoms. And this can occur just as it occurs for alkanes, but these are maybe less common. The most important reaction is the addition reaction, where atoms get added to the alkene where nothing else gets replaced. And so you take an unsaturated system and you make it saturated. Now, the reverse of reaction 2 is where we do an elimination reaction. And in this case, the atoms are actually removed to produce an alkene. So we'll look at that as well. So here we have a double bonded system, carbon-carbon double bond in A, and we react with some molecular system XY. The XY bond breaks, and we form a bond between carbon and X and the adjacent carbon and Y. And in general, alkenes are more reactive than alkanes. Like we said before, alkanes are pretty unreactive systems, but alkenes react pretty quickly, or I would say more readily, by these addition reactions. So we've formed we actually break one carbon-carbon bond because we start with a double bond and we end up with a single bond. And we produce a carbon X and a carbon Y bond. There are a lot of types of alkene addition reactions, but there are 4 important ones that we're going to consider. The first one is addition of hydrogen to an alkene. And you might be able to guess what that produces. That'll produce an alkane. So this is what we call a hydrogenation reaction. We can also add a halogen. So this is a halogenation reaction where we add, for example, bromine to, we form 2 carbon-bromine bonds or 2 carbon-chlorine bonds. There's a hydrohalogenation reaction where we take a hydrogen halide like HCl or HBr or HI or HF, and they add to form the corresponding alkyl halide. And then finally we can add water. And we've got an H and an OH in water, and one carbon picks up a hydrogen and the other one picks up an OH group. So predicting the reactions is not about memorization, but about balancing the equation, make sure the carbons all have 4 bonds after the reaction is complete. That'll be an easy way for you to understand, and from that you may be able to deduce what all the reactions are at this point. And of course, chemical equations need to be balanced even when written as structural formulas. So this is a type of This is an important type of chemical synthesis. Medicinal chemists use this all the time. Material scientists use these reactions all the time to produce new structures. So let's look at each of these reactions. Like we said, our first reaction, we take our alkene, we react with hydrogen via our hydrogenation reaction. We add a carbon-hydrogen bond to each of the carbons, and we break one of the carbon-carbon double bonds, or the one carbon-carbon double bond. And so again, we end up with each carbon containing 4 bonds. Our halogenation reaction adds a halogen across the double bond, in this case forming 2 carbon-bromine bonds. In C, this is a hydrohalogenation reaction to form an alkyl halide. And in this case, this would be ethyl bromide or bromoethane. And then the final one, when we add water, we typically use, and notice in part A we needed a nickel catalyst. We can use a nickel or other reactive metal catalyst to break up the hydrogen to get the reaction to proceed. And then if we add an acid catalyst, that helps facilitate the addition reaction of water to an alkene. And this forms a structure that we call an alcohol, and we'll discuss alcohols in our next chapter. So here we're taking ethylene, adding water with an acid catalyst to form ethanol. Each of the 4 types of addition reactions has a name, like we've been saying up to this point. Addition of hydrogen is hydrogenation. Addition of a halogen is halogenation. Addition of a hydrogen halide is hydrohalogenation. And addition of water is hydration. So this table here summarizes each of these processes, the alkene reacting with the appropriate reactant, and our product, what is generated. And the catalyst is shown here, and you should know all of these. An important thing to consider is how the alkene is added. So everything we've looked at so far when we're working with ethylene is only one possible product. So the hydrohalogenation of ethene shows us that we get bromoethane. When an alkene is unevenly substituted, if it's a larger carbon backbone, there can be multiple different products when you do a hydrohalogenation or a hydration reaction, because you're adding 2 different species to a carbon atom. And this leads us to something that's very important. It's called Markovnikov's rule. And the easiest way to understand it is the rich get richer, or them that have, they gets. So thinking about this in a molecular term, when an alkene is unevenly substituted, that is, the carbons don't have the same number of hydrogens, there'll be a major product, and the major product is the one that's formed in the greatest abundance, and there'll be a minor product that's produced in small amounts, sometimes insignificantly small amounts. So according to Markovnikov's rule, the hydrogen of the hydrogen halide preferentially adds to the alkene carbon bonded to the greatest number of hydrogens. The halogen binds to the carbon with the fewer hydrogens, so the one with the most hydrogens gets more. If we look down here at our reactant in reaction in figure 12.9, this illustrates this. We have propene. Propene reacts with hydrogen bromide. Our major product then is 2-bromopropane, and the minor product is 1-bromopropane. The hydrogens are preferentially added to the carbon that already has the most hydrogens. Similarly, in hydration reaction, we have Markovnikov's rule. So when we add the hydrogen from the water, it goes to the alkene carbon with the greatest number of hydrogens. The OH preferentially goes to the carbon with the fewest hydrogen atoms. Again, taking propene with water and an acid catalyst, then we tend to produce 2-propanol. That's the major product. 1-propanol is the minor product. Elimination reactions are the reverse of addition reactions. They remove atoms from an organic compound, resulting in the formation of a double bond. The atoms are removed from adjacent carbons, resulting in a double bond. An elimination reaction has a single reactant, but can have multiple products, making it a type of decomposition reaction. So depending on how the elimination occurs, you can get multiple products. So here we have a substituted alkane system with an X and a Y on it. When these are eliminated as the molecule XY, we've produced a carbon-carbon double bond. So this is simply the reverse of the addition reaction. Addition-elimination reactions are one of many types of what we call reversible organic reactions. That is, ones that go back and forth, and you can push the reaction in one direction or another depending on how you control your conditions. So we're not going to cover this in this course, but in biological chemistry you will go through how reversible reactions are important in biological process called metabolism. So it turns out in your body, glucose is both broken down, and that's in a normal metabolic or fed state, but it's also synthesized during fasting conditions in your body. So glucose can go to other compounds plus energy during metabolism, but your body can take other compounds plus energy and in the fasting state produce glucose. All right, now we're going to look at another important process for polymers, and this is one of the major processes that industries use throughout the world. And these are what are called alkene polymers, produced by polymerization of alkenes. So what is a polymer? A polymer is an extremely large molecule, and it doesn't have to be extremely large. They can be, middle-sized molecules, but they're generally molecular weights of a few thousand to many millions, or tens of millions, or a billion. So molar masses in grams per mole that are very large, up to very large values. So they're large molecules that can be made from, it says here hundreds or thousands, but there can even be tens or hundreds or thousands of repeating small molecule units joined together called monomers. So common polymers include a lot of plastics and synthetic fibers that we use, like Teflon, polyethylene, nylon, polyester, polycarbonate, and so forth. So alkene polymers are going to be polymerization of alkene molecules. Now we're going to look at addition polymers. An addition polymer is a type of polymer that's formed from alkene monomers via addition reactions. Now, the important thing to understand is when alkenes polymerize, you don't end up with an alkene in the end, you end up with a different structure. And we can see that here. So in addition polymers, the monomer molecules add together by shifting their electrons from their double bonds to form new carbon-carbon single bonds, connecting the different monomer units. So the common name for polyethylene, the common name for ethene is ethylene, and that is the name from which we derive polyethylene. And so you can see in figure 12 here, you've got 3 different ethene molecules, or ethylene molecules. If you take the first ethylene unit and you break one of the carbon-carbon double bonds, and then you take the second unit and break one of its carbon-carbon double bonds, the rightmost carbon on the left molecule and the leftmost carbon on the right molecule can form a single bond. The same thing can happen with the third molecule, and you produce a linear chain of carbon atoms. Notice that in polyethylene, you're actually having a saturated hydrocarbon. So really polyethylene is a big alkane is what it really is. So N in this case can be very large. Yeah, sometimes it can be small. In fact, in our lab, we've handled polyethylene that's smaller, maybe with hundreds of units. Maybe 100 units or 50 to 100 units. So not a particularly large molecule, but the molecule, the polymer, behaves like an alkane because it is an alkane. But we call it polyethylene because it's a polymer of ethene or ethylene. Polyethylene can exist in different forms. There's high density polyethylene and low density polyethylene. And it depends on how the structure is made. The reaction conditions to produce polyethylene can produce these two structures. Low density polyethylene tends to be highly branched. So if you think about this, imagine you took a bunch of straight chain units and let's say you made a bunch of molecular models and you made a polyethylene chain that was linear and made a series of these, maybe 4 or 5 of these. You could stack them together quite nicely. But if you branched the polyethylene, then it wouldn't stack so nicely. And when it doesn't stack very nicely, there's space between the chains or layers. And so low density polyethylene tends to be a highly branched system and experiences weak intermolecular forces. So low density polyethylene is highly branched. And this is where you want to use flexible polymers like plastic bags, in the grocery store. High density polyethylene is the unbranched system, and the chains stack together nicely. The material is more dense and more rigid, and this is used for a lot of plastic bottles like milk jugs and so forth. Not all plastic bottles are polyethylene. Some are other polymers that we won't discuss. So there are other types of addition polymers. They're based very often they're based on substituted polyethylene. So if you replace the hydrogen atoms in ethylene with fluorine, so if you have tetrafluoroethane and you polymerize that produces something called Teflon. And you may have handled Teflon or used Teflon cookware before or had Teflon coated systems. We have Teflon reactors in our lab. We use Teflon liners for highly reactive, very corrosive systems. And what you've done is when you replace the hydrogen with a fluorine, the fluorines on the outside then become very resistant to other materials. So the polymer becomes non-flammable and it does not oxidize, and it does not readily thermally decompose. So we'll look at some addition polymers in a bit, and you can see this here. So polyethylene, polypropylene, polyvinyl chloride, polystyrene, and Teflon or polytetrafluoroethylene. These are different types of polymers, and you might try drawing out the actual a little piece of the polymer structure based on these various monomers when they undergo addition polymerization. It'd be useful to do that. And you can see some of the common uses for each of these systems. These polymers are all produced in extremely large quantities every year worldwide. Next, we're going to look at what we call aromatic hydrocarbons. Aromatic compounds are kind of a unique and special group of compounds. They have hydrocarbons that are in a ring system where it is unsaturated. And this creates a unique situation. So look at figure A in our slide right here. So figure A has 6 carbon atoms in a ring. Each carbon has exactly 1 hydrogen. Each carbon has one single bond and one double bond. But it turns out you could redraw this structure and flip all of the carbon-carbon double bonds to single bonds and all carbon-carbon single bonds to double bonds, and you'd have an equally good structure. So the question is then, which Lewis structure is right? Well, it turns out neither one is. The actual structure is the average of the two. Each carbon-carbon bond is a 1.5 bond in this system. And so what happens is the electrons move around like a ring. So this is what we call delocalized double bonds. And oftentimes you'll see benzene drawn as structure B. That would be the kind of the line structural representation. But most commonly they're drawn as C. We draw the circle to remind ourselves that the carbon-carbon bonds are all equal. They're not single and double. They're all 1.5 bonds, and the electrons move around freely. Remember, the electrons are quantum mechanical particles, and while there are sort of boundary conditions with the atoms, if there are two identical ways they can be, the electrons will sample both of them equally. Now, the most common aromatic ring is this benzene ring that we've shown here. But there are a whole family of different types of aromatic structures. And there are all cases where there are 2n plus 2 extra electrons. So in this case, if you look at benzene, there are 3 double bonds. 3 double bonds corresponds to a total of 6 electrons. So in this case, 2n plus 2, n is 2, so we've got 6 electrons. Anytime we have a ring structure that's closed and has 6 electrons, it behaves like an aromatic system. So it doesn't have to have just 6 atoms. You can make these structures with 7 atoms or even 5 or more. So we can have 6 electrons, we can have 10 electrons, and in fact you can have 2 electrons, it turns out, as well. Those are much harder to make and more unusual, but the most common one we're going to find is benzene. That's the one we're going to work with in this course, and it's a good one to think about. So here we see the single and double bonds are alternating, but in reality the electrons are actually delocalized. They're really spread out throughout the entire ring, and we have kind of lots of different ways to measure that and see how the electrons behave. So here's our summary of hydrocarbon families. The alkanes, everybody only contains a single bond, and these are saturated systems. Alkenes contain double bonds, and they are unsaturated. Alkynes have triple bonds, and they're unsaturated. And aromatics contain, and it says here they contain a benzene ring, but there are other ring systems that are aromatic. They are cyclic, unsaturated systems where you have 2n plus 2 delocalized electrons. So here's our aromatic structure for benzene. The structure is trigonal planar. If you look at each of the carbons, they have 3 electron groups or 3 electron domains. That means that they are going to be flat. They have 3 electron domains, and there's approximately a 120-degree angle in there. And in fact, it is a 120-degree angle for benzene. It works out nicely for this system. So it's a flat molecule. It lays down flat on surfaces and shows the behavior of a flat system, flat molecules. Now, it turns out that you can substitute onto the ring, so you can replace the hydrogen with other atoms. And there are 2 types of substitution reactions. There's nucleophilic substitution and electrophilic. We won't go into those details, but we can do substitution reactions, and you can have mono-substituted, you can have di-substituted, you can have tri-substituted systems. You can have tetrasubstituted, pentasubstituted, and hexasubstituted systems. You can substitute all 6 hydrogens on there if you like. So a common molecule you may have heard is TNT. It's an explosive, trinitrotoluene. It has 3 nitro groups on it. Monosubstituted benzenes are named just by putting the substituent name on there. So, for example, if we put a methyl group on there, we would call that methylbenzene. But that's most commonly called toluene. The name is actually so common that you won't see methylbenzene used virtually ever. So if you look on if you go to purchase something, you always purchase toluene. So methylbenzene is toluene, just like no one goes to buy dihydrogen monoxide, they buy water or obtain water. So if we put a bromo group on there, we would have bromobenzene. If we put a chloro on, we'd have chlorobenzene. If we have 2 or more substituents on the benzene ring, we have to indicate the numbers. So the carbon bond to the substituent that comes first alphabetically is designated as carbon 1, and the others follow alphabetically, going with the smallest possible numbers. So you can see here in the figure, in A, we have bromine and iodine. Of course, bromine's first in the first in the alphabet. So we would designate the bromine position as 1. The iodine position would become 3. So we call this 1-bromo, 3-iodobenzene. And if the substituents are the same, again, we do the same thing, but then we would put a di in front of the names. So benzene can also replace a hydrogen atom. And when you do that, you call that a phenyl group. And here's kind of a crazy looking molecule. It's got 7 benzene rings on it. You have 1 central benzene, and then all the hydrogens on the central benzene have been replaced by a phenyl group, a C6H5 group. Just like you have a methyl group and an ethyl group and a propyl group, we have a phenyl group. And here we have hexaphenylbenzene. There are isomers of aromatic compounds, and this is the case when we have kind of substitutional isomerization, or we can have multiple positions things can be located. And for benzene, we have a special naming system we call ortho, meta, and para. So here is 3 cases to see that illustrate this. You've got dibromobenzene, and there are 3 possibilities for this system. The bromines can be next to one another, they can be separated by an extra carbon, or they can be separated by 2 carbons. So we can have 1,2-dibromobenzene, 1,3-dibromobenzene, and 1,4-dibromobenzene. And when we do this, sometimes you'll more commonly see the nomenclature ortho, meta, and para rather than the numbers. So ortho indicates that the substituents are adjacent, meta indicates there's 1 carbon difference, and para indicates they're on the opposite side of the ring. So here's para-dibromobenzene. Now, like we said before, toluene is the more common name for methylbenzene. It's the one that is used in patents and publications and on on safety sheets and in procedures. We'll call this toluene. And so whenever we have a system that has the methyl group on it, we can call it toluene. And then, of course, if we did substituents on the toluene ring, then we would put the right nomenclature there. So, for example, if we had nitro groups in the 2, the 4, and the 6 position, that would be trinitrotoluene. That completes our study of alkenes. We'll go through more detail in class lecture.